just solve a problem if I don't know what I need to know. I need to understand. I need to have the understanding of the problem I'm solving, which means I need to know the assumption that was violated before solving a problem. Now, because of that, I want us to revisit the assumptions of linear regression. Okay. Now, I don't know whether I'm actually going to politics this time around. Okay. Where I want to focus on Republican candidate in 2016 and the Republican candidate in 2012. I mean, the presidential candidate in the United States, and of course, X represent the percentage of voters that voted for Republican candidate in 2012, and of course, and Y is going to represent the percentage of voters that voted for Republican candidate in 2016, and of course, the Republican candidate in 2012 was, I think, of Senator Mitt Romney, and then in 2016 was the former President Trump. Okay, now this is the map of the United States. Okay, if I decided to, fit a linear relationship between X and Y, the X and Y, if I want to use, I'm trying to characterize a relationship between the percentage of votes received by a Republican candidate in 2012, okay, in relation to what he received in 2016. And I'm deciding to use all counties in the United States except the one in Alaska. Okay, except the one in Alaska, of course, it means I'm actually going to be using population regression model. That is not a sample. Okay, using most of the counties in the United States, of course, the parameters we're going to have, the regression parameter we're going to have is basically going to be very, very close to the truth. Okay, so with that, we're going to use population regression model. And, if you take a look at the scatter plot that I'm actually showing you now, okay, it's plotting the percentage of votes received by Republican candidate in 2016 against the one received by Republican in 2012. And if I have that regression model, I have a beta naught to be 4.424 and the beta 1 to be 0.990. Of course, since I'm using most of the counties in the United States, of course, these guys here, they're going to be true parameters. And of course, I can, conduct an inference. Of course, I'm actually going to rely, on this parameter. They're going to be reliable because I'm actually using, very close to the entire counties in the United States. And I can answer a question on inference, okay, 50% of the voters in the county voted for a Republican in 2012. Okay, I can answer a question of what percentage of voters from the county would vote for a Republican candidate in 2016. Of course, the Republican candidate in 2016 was actually the former President Trump. And all what I'm just going to do is just to plug in that 50 into the model. And of course, I got 53.924%, and I can authoritatively say, okay, 53.924% of the voters in that same county. Don't forget here, my observational unit is county, okay? This county. So, so 53.924% of the voters in that county is expected to vote for Trump. Don't forget, look at what I use, is expected. That's a mean, that's an average, okay? Now, but what if I want to ask this question? I'm not talking about expectation anymore. I'm talking about what is Y giving X equal to 50. Okay? Now, if I want to ask this, I'm basically going to be talking about the idea of sampling distribution. Because if I want to answer that, so that was why. So what I'm going to do now is this. If you have this plot, and you now see that most of it is called scatter plot because you don't expect all the point to be on a straight line. We expect some deviation, right? But if the majority of the points are close to the line, okay, what does that mean? Okay, and if they are far from the line, of course the error exists. It is because of the error that was the reason why all of them don't why they are not on the line. Don't forget, we're using a model that has error, right? we've already acknowledged the fact that there's going to be error, right? Okay. Now, if you take a look at that multiple choice, I said, okay, dash of them are close to the population line. Okay, more of them are close and fewer of them are far away. Okay, and of course, the most observation that do not land on the population regression model becomes error, even though if you are fitting, if you're using the whole data set, there's still going to be error. Okay, now, if you take a look at that now, because of that, now the question now, what is the implication of assumption? I told you the other time in this class, assumption for linear regression actually center around error. Okay, and let me tell you this: if you solve one problem, there is possibility you might have solved another problem, but that is not a guarantee. I remember I said it in this class. If somebody is being tried on a 5-can charge, right? If it's free on one charge, that does not mean it's automatically free of other charges. You get what I mean? Okay, so, and, assumptions affect the properties of estimator. Okay? And when I say it means, the implication of assumptions on regression parameter is huge. Okay? So if assumptions are violated, you may not be able to trust your regression parameters. You may not be able to trust the standard error associated with the parameter. Because don't forget, you need a standard error, right? To conduct inference, right? Inference like what? You may want to construct a confidence interval around the parameter. Not only that, you may also want to conduct an hypothesis about the parameter. Okay, the standard error you are using, if it's problematic, you are not going to get a good result, and you could mislead. Now, what are these assumptions again? I'm revisiting that: linearity, independence, normality, and equal variances. We've done this in class, and you know what? I need to revisit these assumptions so that you will be able to know, your level of intervention in terms of power transformation, because the type of power transformation you basically going to adopt may depends on what assumption is violated. And it's just like, okay, you are arresting me, right? You are arresting me, right? I think I need to know my offense. Okay, I need to know my offense. If you punish me, I need to know my offense so that if I go back to the society, I'm not going to repeat the same. That's what we mean here. Okay, now, there's something I'm actually going to tell you now in the implication of this assumption. There's something I wanted to say here. When you look at the assumptions of linearity, okay, if the expected value of error equal to 0, what that means is that linear relationship exists between the two variables. When errors are independent, then what that means? It means the response given any values of the predator will also be independent. I'm going to say that again. When errors are independent, then it means the response given any values of the predator will also be independent. Now, when error is normal, okay, when error follow normal distribution, right? Then what is the implication of that? It also means the response variable given any predator will also be normal. That is an implication, right? Now, when error has equal variance, then what does that mean? Then the conditional variance, like the conditional variance of the response given predator, we also have a constant variance. That is what it means, right? So, and when something affects the error, automatically it will affect the quality of the model. That's exactly what we're saying. Okay, now because of that, you're going to see something now. When error follow normal distribution, the response variable given x also going to follow normal distribution. This is the mean. The mean is beta naught plus beta 1x. The variance is going to be sigma squared. Error also follow normal distribution, but the mean of error is 0, but the variance is sigma squared. Now take a look at it. The two of them follow normal distribution, only that they have different means, but they got the same variance. That is an assumption, right? Okay, now because of that, I'm actually going to impose, I'm going to say, okay, since the assumption associated with the error is they are all met now, then I'm basically going to say, okay, on the other hand, I can impose those assumptions as well on the response variable. Okay, I'm going to say, oh, the response variable given predator is also going to be normal. Okay, it's also going to have a conditional independence, and at the same time, it's going to have an equal variances. Okay, that's what we mean. Okay, now back to the example on, on the distribution. The one on the percentage of votes received by Republican candidates in 2012 and 2016. Initially, we used a population regression model. And the idea behind using the population regression model because we actually investigated most of the counties in the United States, except the one in Alaska. But let me tell you, in a real life, practical situation, we may not have access to all those data sets. We may want to take a sample, right? Now, because of that, I'm actually going to walk you through the idea behind sampling distribution of the least square estimators. When I say least square estimator, I'm referring to regression parameters. I want you to see how they actually conclude that the distribution of regression parameters will be normal. Okay, they are not just normal. They actually need to do something before they can be normal. Okay, so that when I explain this, then you can see the difference between this and bootstrapping. Because when you take a look at this and bootstrapping, oh, we're more or less like doing the same, but only that with bootstrapping, I'm only focusing on the sample. But with sampling distribution now, I'm not focusing on the sample. I'm focusing on the population. Only that I go into population so many times, take a sample, compute the characteristics of interest. Now you're going to see now. I have a population model, right? But I can only use population model if I have a lot of data. If I have the whole population before me. We don't have resources for that. We're going to generate data, right? We generate data, sample of data, right? Now, Y and X here is more or less, I actually want to talk about response and one predator, right? Okay. Now from there, I'm going to fit. We normally mention fit when we're talking about sample. You know that, right? Okay. We're going to fit a model, okay, for that. And at the end of the day, now take a look at the difference between the y equal to beta naught plus beta 1 x plus the error, and the one that have a cap. The one that have a cap means we're working with sample, right? The one without cap means we're basically working with the entire population. Of course, earlier in this course, I've walked you through how you can estimate the parameters, but that is not where I'm going. Of course, I gave you an example the other time when you are trying to talk about the timing of production run, where you are trying to characterize a relationship between production quantity and the runs time. Okay, of course, you are not going to use. You don't need to use every data set. You can take a sample size. Here, they take 20. Of course, you fit the model. But let me tell you this. If different researchers should go into this company and they take sample size randomly, they're basically going to get different results, which I want to demonstrate now. Take a look at that. The first researcher go there, take a sample, fit a model, get a beta 1, beta naught. Another researcher go there, get a different result. Oh my God. Take a look at that. Here, this is different from bootstrapping. Here, we have new information from population. We keep going back, right? But in the case of bootstrapping, oh my God, you don't have anything to do with population anymore. You focus on the sample. Whatever manipulation that you want to do would be on the sample. Does that make sense, right? Okay, now the question now, how good are your estimated slope and intercept here? Because you got different values for beta 1, you got different values for beta naught. But let me tell you this. And also I said, how much can you trust the method of linear regression using fitted model to make inferences about the population model? If we have enough resources to study everybody, there's not going to be any issue. Okay? But right now, the essence of inference is just like, oh, I take a sample, right? And based on the my observation on the sample, I actually want to generalize on the entire population. Okay? Now, there's something that now in this case now, the beta one, they vary, then they become random variable. The beta naught also varies, they become random variable. Then I will need to get their probability distribution. Why? Why do I want to get their probability distribution? Because I want to know what is the measure of central tendency or the measures of location I'm actually going to use. Because am I going to use mean or median or mode? Before I can use mean, the distribution has to be normal, right? Now the question now, the value, the different values that I get for beta 1, that I get for beta naught, are they normal? Of course, we have a way to investigate that in statistical analysis. Okay, now, because of that, let's say there's a researcher called Jack. Oh, Jack decided to go into counties in the United States and only choose 10 sample, and he estimated the beta naught and the beta 1. Jack has a result. The beta naught for Jack is 2.763. The beta 1 is 1.004. He actually, take a sample of 10 counties, 10 equal to 10, right? And the one in the red line is a population 1, which is a true value. Now you can see the deviation, right, of Jack result compared to the true value. Okay, now and then that's what we have. Take a look at that, and that was why I said the estimated coefficient in the fitted model could be different from the coefficient in the population model. And you know what? Let's say this time around, different person, not only Jack, also go to the population. Okay, even though if they are taking the same sample size, they're still going to have different values. Take a look at the intercept for the first one, 2.763, right? Even here, the intercept is negative. Okay, that's bias, right? Compared to the true value, okay, that we have here. Okay, now when you take a look at what we have now, and that was why I said the estimated coefficient in the fitted models could be different from sample to sample. We've already acknowledged that fact. Okay? Now, the summary now of that. I said the estimated coefficient, which are the values of the beta naught and beta 1 based on the sample in the fitted model, could be different from the population, coefficient. The population coefficient are the true values that we're actually looking for. Okay, and I said the estimated coefficient, beta naught and the beta 1 based on the sample in the fitted model could be different from sample to sample. Not only that, they're going to be different from the population value, they're also going to be different from sample to sample. We've acknowledged that fact. Okay, now, for us now to harmonize situation, what are we going to do? Then the estimate of beta naught, which we call the intercept, and the beta 1, which we call the slope, they are now going to be treated as random variables because it varies from sample to sample. And because of that, we're basically going to exploit the idea of probability distribution. And why do we need a probability distribution here? Because we have different values of beta naught, we have different values of beta 1, and we basically want a particular value to represent. We don't just choose. We need to be statistically guided, and that is the reason why we're seeking to know the probability distribution. Okay, now I wanted to take a look at this now. I'm going to show you the idea of sampling distribution now. Okay, for the sample size of 10 counties, okay, the numbers of time you go to choose is 2. Here now, I'm talking about replication now. In bootstrapping, right? You remember, or we also have replication, right? Good job. Now, take a look at what we have, okay, and that's of the fitted. Now, take a look at this. Somebody has a question in this class one day, and he said, when the numbers of repetition increases, that could contribute to the quality of the model. Yes, that's what I want. Even in sampling distribution, that's what I want to demonstrate now. Okay, even though you are choosing the same sample size, 10, 10, but the number of repetition here is 2. The numbers of repetition here is 200. Of course, that of the 200 will make more sense. Okay? And for us to be able to show this, when the numbers, don't forget, I want to want to exploit the distribution of the on beta 1. Don't forget, why are we exploring the distribution on beta 1? We're looking for a threshold that we enable it to attain normal distribution. That's what we're looking for. I'm going to say that again. We are looking for a threshold, like what is the number of repetitions that I'm actually going to make before this can attain normal distribution. Don't forget, in the first place, okay, the normal distribution can only be attained when we work with large sample, right? Now, take a look at this. I'm working, but I don't have large sample. But what I'm trying to do now, when the sample is 10, but I repeat, sampling distribution, okay, the number of sample, when it is 20, let's see the distribution of the estimated slope. It's looking like that. Is that normal? No. When I'm displaying now, that's an histogram, right? Your histogram is one of the graphical way, okay, to investigate normality. Okay. Now I'm still working with 10 county, and I want to go into uh, the number of sample to be 200 now. Oh my God, it's taking shape now. Take a look at that. When I increase that to 2,000, look at that. Look at that. So what this is actually telling you now is trying to tell you that is slope that we have. Okay. Here you got 20 slopes. You got 200 slopes. You got 2,000 slopes. And of course, you can see the distribution. Okay, the sampling distribution that we're trying to do here. We're exploring the distribution in a way. We basically want to see the one that will give us a normal distribution. And that was why I said, what if the number of sample approaches infinity? 200 is like that. We don't need to approach infinity. Okay, we can just stop at a reasonable, because it's going to get to a point. If 2,000 can actually give me normal, why am I going for more? Okay, so that was why now we're exploring the distribution of beta 1, and because of that, we're basically going to say, okay, you know what, based on what I'm seeing now, beta 1 as a normal distribution, and the expected value of beta 1 equal to beta 1, the expected value there is just like the average of all the slopes. Okay, the average of all the slope is basically going to be the true value that we're looking for. That's what that guy means. Okay, I wanted to take a look at that. But what if in a situation where the numbers of sample now tend to infinity? I've already told you the other time. Of course, when the numbers of samples actually increases, of course, you're basically going to see that the shape is actually going to approach a perfect normality. But you know what? We don't need to get a perfect normality before we can actually make a meaningful inference. Okay, go ahead.
I get that mathematically going like to infinity makes sense. But let's say like if we are doing 2000 repetitions, I just looked up like in USA there are like 3000 counties. But if we take 10 counties 2000 times for sampling, that essentially goes to like 20,000, right? So uh, theoretically, like with respect to the context of the problem, do we stop any place before uh, like theoretically, because let's say if there can only be 10 planets, so we can't take a sample for 100 planets, right? So do we stop somewhere theoretically before, like obviously going to infinity will give me normal distribution, but do we have a theoretical limit as well while solving for this?
Oh, you mean like probably we have a kind of threshold, right? That we can actually say, oh, yeah, because of what you said, we now give a formula. And theoretically speaking, just like what you said, a lot of stuff happen behind the scene, right? Now, achieving the threshold that you said, we now derive a formula that we use in statistics now. And before we can use that formula, even though we're going to go into the population once, right? But that very formula, because we have proved theoretically, that very formula we actually present to the world as if we've gone into population so many times, but there is a condition in the formula. The formula says, okay, you know what you need to do? Take at least story. Now, I'm going to show you what you are trying, because just like what you said, initially we tried 10 sample size, but before we attain normality, you know what happened? We have to increase the number of repetition. What of in a situation where I just want to increase the sample size a little bit, and I'm not just going to use a lot of repetition? Which one is going to land me? Which one is going to take me? And that's exactly what we want to do next. If you look at the next one, I'm going to show you what I'm doing here. You know what I'm doing here? The number of repetition is the same, right? 200. But the number of sample, okay? Give me 1 second. I think there's something I'm missing. Okay, the number, if you take a look at this, I choose 10 counties. Sample size here is 10. Oh, 50 counties, right? And the number of repetition for two of them is 200. Then I think I'll just go for, you can see this is out of this and this. Which one do you think very close to normality? Exactly. So, which means at times we can reasonable, okay, talking about sample, adjusting the sample size, and also adjusting what we call, the repetition. But you know what? The central limit theorem said, you are good if the moment your sample size is 30. I'm going to write that down. And greater or equal to 30. Okay? Now, and because of that, I'm now going to show you, I'm going to show you something. Okay, now take a look at what I have. I'm going to show you this. You've seen it before. Do you know this? The formula here, that is the variance of this guy. This particular formula will give you a fantastic result if the sample size is at least 30. This has already been proved. Because the beta naught, the beta won't follow normal distribution now. The idea of a sampling distribution has already been used. But provided your sample size is at least 30. Why do we go into bootstrapping? Why do we go into the other intervention? Because we have a small sample size. If we don't have a small sample size, of course, this can be trusted. Does that make sense? So you don't need to worry yourself about, oh, you want to do sampling distribution. You don't need that. You only need to focus on this. Because a lot of things that happen behind the scene, okay, led to this. And the only way you can trust this, when the sample size is at least 30. When the sample size is not at least 30, then this cannot be trusted. The variance of the beta naught, the variance of the beta 1, they are no longer going to be appropriate. Okay, so, and that was why I actually said here, okay, take a look at this. What happens when the sample size increases? Of course, when the sample size increases, part of what happened behind the scene, we showed you the other time. When sample size is increasing, you can see the shape of the data set, of the slope or whatever regression coefficient, the shape is going to be approaching normality. That was why we said, what happened when the sample size increase? Okay, the mean of the distribution does not change. Okay, does not change means it converges to the true mean, or very close to the true mean. What happened to the variance? The variance of the distribution usually reduces. We want that. When the variance of this and this it decreases, you know what is going to happen to standard error? It's going to go down as well. If the standard error goes down, you know what is going to happen to your inference, particularly when you are testing hypothesis. Don't forget you're going to use your test statistic is going to be estimate divided by the standard error when the denominator is actually very, very small. What do you expect from the test statistic to be large? When the test statistic is large, the p-value will be small. When the p-value is small, what is going to happen to the predictor? It will be significant. And not only that, if you want to do the confidence interval, you need the standard error as well. When the standard error is very, very small, what is going to happen to the range of the confidence interval? Oh my God, they're going to be so narrow. That's what we want. Okay, now the implication of using filter regression model to approximate population regression model, don't forget, initially we're supposed to work with every data, but we don't have resources for that. And you know what we're trying to do? We're using filter model to approximate population regression model. Okay, now we expect the estimated coefficient to be unbiased. What do we mean by unbiased? That is when the expected value of this equal to that. The expected value of this equal to that. That's what we mean by unbiased. Then as sample size increases, it is more likely to get an estimated coefficient that is close to the parameter value. Don't forget, the parameter value is the true value, the one you get through the population, right? But don't forget, you don't have resources, right, to study the entire population, right? And what we can do is to increase the sample size, right? And that has already been demonstrated. So take a look at that. Okay, now, that's going to be the end of this particular lecture. And you know what we're going to do on Wednesday. I'm now going to be walking you through how we can actually fix a linear regression by transformation. And let me tell you this time around, the transformation, you've seen some regression model before, the one that have a log, right? You're going to say, oh, log of the response, or the log of the predictor, or one has a square root, or the other one. How do we just put a log on something? What are we trying to fix? Okay, that will be the next story. You know, I told you the other time, statistics is like a story, okay, and it goes on and on and on. So, like I said, this is where I'm actually going to stop today. I'm going to start grading the midterm one makeup tonight. And of course, by latest Wednesday, your result, your grade will change. And the moment you see your grade, for those of you who earn extra credits in my class, if you want to spend it now, on the midterm, you can send me a message. Oh, I want to spend my extra credit on the midterm now. But if you don't want to spend it now, you can save it. But I also need to get information from you. Oh, I don't want to spend my extra credit now. I want to save it for the future. That's no problem. It's your extra credit. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.